chatting with our own data, using our own data is what it's all about. Now, I don't know about you, but I copy and paste things into ChatGPT or Claude all of the time to get some responses. But of course, it doesn't know about my own custom data. That's what we want to do here. Using LangChain will allow us to have custom data that's not just a small snippet, but really big pieces of data that we chunk down and then store into a vector database. Welcome to Try LangChain. In this course, I'm going to show you how to implement LangChain so that you can actually have your own data set that you have a conversation with, and then you can use an LLM to infer those conversations to help you with the querying and also summarizing of the responses that come through. Now, all of this is driven through a chain of events that happen. So the first thing being you actually create your own vector database with your own actual data set that you turn into embeddings so you can do things like semantic search. You actually don't need LangChain for any of that. But as soon as you want to start querying and having conversations with those databases, then you actually start using LangChain to actually make all of that happen. Now, of course, Upstash provides us with our vector database. It's why I actually partnered with them on this series, is because it makes it really easy to just quickly grab information about your data sets. That's what vectors are all about, as we'll learn in just a little bit. But what LangChain does is it will take that vector database as a piece of the chain. It will then allow you to have your own prompts, like prompt engineering. I'm sure you've heard about that. But the idea is you can tell the LLM, hey, what it is that you're trying to do with your own database. Like what kind of conversation are you trying to have? Once you end up having that, you can then parse it down to being just a simple response back to you. Now, once we have this chain, we can then turn it into a REST API endpoint. And that's another thing we're going to end up doing. The reason for this is then you can actually embed this chain into a microservice that's stuff like Django or another FastAPI project, or even Next.js, or pretty much any project out there would be able to use. We'll be able to use these LangChains that you build. And yes, you can build many of them. You can switch to different LLMs as well to make it even better. And that's what's going to happen over time. I'm really excited about where LangChain is going, but let's go ahead and take a look at the demo in just a moment. My name is Justin Mitchell. I'm going to be walking you through this step by step. And yes, I partnered up with Upstash, so thanks to Upstash to help make this course happen. But I'm really excited to show you what's going on. So let's take a look at the demo right now. Here's what the course is all about. Now, I'm in a Jupyter notebook from the very last lesson, but the idea here is using LangChain and LangServe to have a micro API service that we can send questions to, like what is NY? Now, of course, if you are a person, you probably know what NY stands for, but this actual AI does as well. But what if we said something like, what is LA? Now, you might think that this is going to give you a response as well, and it does give you a really good response. But the thing is, it's not going to give us that much information about LA because, let's see, tell me about LA. And I can run this, and essentially what's going to end up happening is it's going to say the provided context does not contain this information. But it does have New York City, which is pretty interesting. So the question is, how do we get to this point? This is all about having conversations with data that you decide. And in this case, it's using something called LangChain that allows us to build a full-on REST API service using FastAPI to actually give all of this stuff working and making it work well. Now, of course, all of the code is already on GitHub, so you can go through this process. And we go step by step building out this whole thing to make sure that LangChain ends up working. And then we use Upstash Vector to store all of our database and all of our data that we might want for, like in our case, we used Wikipedia to actually store some of the data in here. And you can see how it's being used in these different notebooks as well right now. Feel free to go through them. They are in order, so 1, 2, 3, 4, 5 is how we end up doing it. Notice that I use this Wikipedia package. It's an older package, but it does a simple job of scraping data from Wikipedia. In this case, it grabs New York City, and then we also had another city in here as well, Boise, Idaho, which is right by where I am. So we actually go through all of that data, all of that content, and then we turn it into vector embeddings. All of those embeddings are stored in, of course, our partner on this one, Upstash. So you actually go into Upstash, you store everything into a vector database. These vectors are well talked about, but basically they're numerical representations of our text in the context that it stands. We don't pay anything for this because we don't hit the limits at all. We also use Redis for the LangChain rate limiting API service, as you'll see in this course. But the idea is we get all of the data we want. Then what we do is we chunk it down so that we have all of the data, not just part of the data. So it's chunked into different pieces that are then stored into our Upstash Vector Database. Then we can actually do things like semantic search just in the vector database itself. This is where all of that data is coming from, where it says it does not contain specific information about Los Angeles. We could have just added it in to our actual LangChain documentation and also into our vector database. So this is a key part of it, is actually being able to extract large amounts of data that we can then talk about. Now, the cool thing about this as well is the data sources don't matter so much. You can actually have data sources from all over the place. The point is our LangChain will parse our prompts and then be able to actually give us the values here for what that ends up being. So another part of this is inside of main.py. When we actually want to build out a REST API service, it's very straightforward. First off, we initialize FastAPI and also Redis at some point. But the point here is our actual chain. So we grab our chain and then we add routes here for that chain, which you can have a lot of different chains in there. But LangServe, which comes from LangChain, makes it really, really easy to just automatically spin this up into FastAPI. Now, this is the entire application itself right here, with the exception of the chain. The chain is in this helpers.py, which we go over in all of the different notebooks, but we can see that we can use OpenAI's embeddings. There are also open source third-party models that we can use here as well if you wanted to. We use Upstash Vector Store because we need to store these embeddings somewhere. It makes a lot of sense to use Upstash in terms of, well, it doesn't cost anything to learn how to do it. And then the other part is you need persistent data place to store these embeddings. And then the last one is you basically only get charged when you're actually using this data. So if you actually have a lot of data and you don't use it that often, you don't get charged nearly as much as you would. Next up, of course, using LLMs. Same thing. The same idea here, of course, is the more often you actually use this, the more you'll be charged from OpenAI, which ends up being less and less over time. So that number is going to keep going down. But we see a prompt here. This is a prompt that you can continue to update and basically generalize. But the point is, after you get all of that, you can then parse it together with this one single chain. And that's exactly what we're going to be covering. So let's take a look at more in depth of the tool overview to make all this happen. In this one, we're going to be using Python 3, Jupyter, VS Code, Git, Upstash, Redis, and Upstash Vector. We're going to be using LangChain and OpenAI to make all of these things work in conjunction with each other. So a little bit more about the details here. Python 3.12 and the built-in virtual environment manager. Feel free to use other versions of Python or other Python virtual environment managers if you like. I like using the built-in stuff because it's a lot easier for all of us on all of these different systems. Next up, we're going to be using Jupyter as a way to run our code in conjunction with Visual Studio Code. Jupyter is definitely optional, but it's a nice interactive way to make all this happen. Git, of course, is a way to track the changes of our code over time. Now, if you don't know Git, that's okay. You can always just use our Git repo as reference to everything that we're going to be doing in just a moment. Now we're going to be using Upstash Vector as a vector database. If you're not familiar with what vector databases are, I'll talk about them at a high level as well as, actually implementing some of the basics of just building out vectors. The idea here is taking text, like something like serverless data platform, and turning it into a numeric representation of that text so they can compare text against each other. It's a lot easier to compare a list of numbers to another list of numbers than it is to compare a string of text to another string of text in terms of automatically and calculating the magnitudes of these vectors and how closely related that they are. All of that is to say, when we use something like LLMs, we need vectors. We need to turn our text into vectors so we can actually do things like semantic search and all that. Upstash makes it really easy to have all of this work, and it's in a serverless environment. So if you're not using Upstash, if you pause what you use, you're not going to be paying for it. You're only going to be paying for what you end up using, which is really nice. Now, LangChain itself is a way to literally chain together different elements of what you might want to do with your LLMs or with your data. So if you can do a complex query, so something like, what were my top blog posts in Boise, Idaho of 2014? Like, those are queries that you could do with something like LangChain, where it kind of breaks these things apart and it can use all kinds of LLMs to just make that query actually work. Now, what I just said is a little bit outside the scope of what we're going to be doing in terms of LangChain. We're going to be doing a lot of the fundamentals of it so you can build on top of it from here. Now, there is a lot of hype around LangChain for good reason because of how it actually kind of structures everything. So it's like really composable components, really simple components that you can just be like, oh, here's my prompt. Let me take a look at that prompt a little bit more. And then, oh, here's the LLM that I'm using. Let me take a look at that a little bit more. And then from I want to use a search engine results in here as well. I'm going to go ahead and put that into my chain. All of this is going to start to make a lot of sense once you actually start implementing it. Now, we are going to be using OpenAI for a lot of the API services that they have. These API services will certainly change over time, so I'll be sure to point those out when they do change. Now, and of course, so much of this is going to be in our code, so definitely take a look at the code itself. Feel free to jump around as you see fit. A lot of this is about understanding LangChain so you can implement it in a real project. Now, this real project is going to be using FastAPI, but a lot of the things that we're doing here can be repurposed for other Python tools, whether that's Reflex, whether that's Django, whether that's Flask. A lot of the things that we can do is really easy to move those things around thanks to how simple it is to do with LangChain and, of course, with Upstash. Upstash is platform agnostic in terms of if you use FastAPI, Django, or whatever. It's really, really simple and straightforward to do all that, as we'll see here very soon. So with that out of the way, let's go ahead and actually set up our project right now. Open up your command line. If you are on Windows, you're going to be probably using WSL or Windows Subsystem for Linux. If you are on Linux and Mac, you'll probably be using Terminal. That's what I'm going to start this project off with. First and foremost, we want to actually check that Python 3.12 is installed. Depending on how you actually install this, you might need to use a different command to actually check the version itself. I'm using 3.12. The small version or the minor version, that part doesn't matter so much. 3.12 is what matters here. Next, I want to go ahead and check that Git is installed. This actually doesn't matter at all in terms of the version, in terms of what we're going to be doing as well. So what I want to do here is I actually want to clone my repository right off the bat. Now, of course, there's two ways to do this. You could go to my GitHub, and that is at cfe.sh/GitHub. If you go there and navigate into the try LangChain repository, you will be able to see the code that we're going to end up using. So you could always just come through in here and just download the zip file in there. Or if you want to actually stick with us, you would go to the start branch. From that branch, then you would download that code. That's what we're going to be working off of in this one. That's for those of you who don't know Git. For those of you who do know Git, go ahead and grab the repo itself and then just do git clone. Grab that repo, hit enter. Of course, it's going to create the try LangChain folder here. I'm going to navigate into it, and then I'm going to go ahead and do git checkout and start. This is where we're all going to start. Feel free to do this if you like. If you are using your own actual repo that you want to store your own code, just make sure you just run remove rf.git and just remove the git repo and initialize a brand new one if that's what you're going to do. So now with this in mind, I'm going to go ahead and run this project here. So I'll go ahead and do Python 3.12 or 3.12, hit M, venv, venv. This is the built-in Python virtual environment manager. This is the name I'm giving it. Sometimes you see it as .venv, sometimes you see it as .env. I like using venv. I have it on all of my projects. I hit enter, and here we go. It's going to go ahead and create that virtual environment for me. I'm going to go ahead and run source venv ben/activate. Now do keep in mind if you're on Windows PowerShell, it's going to be a little bit different than this. but Windows WSL or Windows Subsystem for Linux, I think it's the same command. Somebody can let us know in the comments. But overall, once you have your virtual environment activated, we run pip install pip -- upgrade. We want to upgrade the virtual environment's Python package installer. There are other ways to install Python packages, of course. I'm using all the defaults because it works most of the time for most people. That's the big reason. Next up, we run pip install -r requirements.txt. Hit enter. This will install all of the requirements we'll need for this project. Now, if we actually take a look at them on the Git repo, we see that there's LangChain and LangChain OpenAI. Now, there are other LLMs that are out there that are really, really good. Claude is one of them from Anthropic. Feel free to switch it out at any point. Once you understand LangChain, being able to switch out the LLM is going to be hopefully very straightforward and easy to you, which will come very, very soon. Great. So those are the requirements at this point. Now, once you actually have all of this installed, just go ahead and run Jupyter Notebook. This should, in theory, work if the requirements had the right installations in there. I'm going to go ahead and make sure that Jupyter is installed by just running pip install Jupyter so that I can have that in there. By the time you're watching this, the requirements will be updated correctly and have the right actual installations, which would include Jupyter. And so now I'm going to go ahead and run Jupyter Notebook, and this should open up that interactive notebook for me inside of my web browser. In my case, I'm using the Arc web browser, but whatever you use is totally fine. So at this point, the Jupyter Notebook is open. One of the things you also might want to do is open up Visual Studio Code, open up the actual folder that we stored this Try LangChain series into. You can open it up just like that. In my case, I'm going to go ahead and save this workspace, and I'll save it as Try LangChain just like that. I will commit the workspace file into Git as well. The other thing is in here, you can create your own Jupyter Notebook. So for example, we're going to go ahead and create a basic chain here very, very soon. So if you do IPython notebook just like that, you will see that you can actually run these Jupyter Notebooks right inside of Visual Studio Code, and then you're going to want to choose a kernel source. So if I import, let's go ahead and just hit import OS and try to run this cell by pressing plus. Notice that it's saying install or enable the suggested extensions for VS Code and Jupyter. Both of those things, I'm going to go ahead and install them in here just so you can see what we're doing. Then our Python environments, you want to grab your virtual environment here. Notice that you can use all sorts of Python environments, including other virtual environments that might be on your system. In my case, I'm using the env bin/Python because that's the local Python virtual environment. And there we go. So now I can run it in two places. I can run it in Jupyter itself. For those of you who are familiar with Jupyter, this is a very straightforward process as well. Notice the code is the same in both places. I'm going to continue to use Jupyter because I think a lot of people that are familiar with Jupyter might want to run it in this location. And if you want to just use VS Code, there, you'll be able to do that as well. With this in mind, let's go ahead and actually create our first chain with LangChain and get that process started. We're going to start off by using large language models the LangChain way. Now, LLMs are plentiful. There's a lot of them out there. So what the developers behind LangChain had to do was make a way that you can just replace any of the LLMs seamlessly without having a huge interruption or disruption to your chain. Now, the chain is quite literally a list of components that all work together that are really easy to swap in and out of, and then you can just run that entire chain and it goes in order, as we'll see. But the first place we want to start is the OpenAI LLM, mostly because OpenAI is probably one of the most fundamentals to many of us out there. Now, there are a lot of providers that are built into LangChain, and there's probably a lot more coming as well. So feel free to experiment with this as you go forward. But the idea here is we want to use the OpenAI one. Now, do keep in mind what we're going to be doing right now is essentially the LangChain version of this on OpenAI's documentation of just bringing in an API key and then running a specific model and then having some chat completion messages. That's it. That's really all we're doing. And so to start implementing this, we need an OpenAI key. So the way we're going to do that, of course, is by going into openai.com. Once you navigate there, you'll go under products into the API itself and then API login here. Once you actually log in, you'll go ahead and create a organization if you have one, and then you'll also create a project, and it'll eventually look something like this. You'll navigate into the playground. So to create the API key, this part will change probably over time because it has, but the idea is you navigate to the dashboard, and then in the dashboard, you'll see that there's this spot for API keys. As you can see, that project API keys have changed from user API keys, which is nice, but also a change that may be unexpected if you've been using OpenAI a little bit here and there. So the idea, of course, is to create a new key here. I'm going to call this my LangChain, let's call it try LangChain or something like that. And I will probably want to have this restricted, but since I'm learning, I'm just going to go ahead and say all, and we're going to go ahead and create this key here. Then we need to verify we're a human. There we go. So I verified it, and now, of course, no problem. I proved that I'm a human to the AI company, which is hilarious. But now that we've got that key, I'm going to go ahead and into my local project, create the .env file here, and we're going to go ahead and do OpenAI API key, and we're going to set it equal to that string there. Now, the reason we use .env is because you never want to inject your secrets into code directly. Instead, you want to use an external file to do that, and that's why we're using this .env here. It's also important to note that .env is gray here on VS Code for a reason. That's because the getignore file has the .env in there. In other words, this file will never be checked into Git or GitHub. You won't accidentally expose the contents of this file, other than if you record a video like I am and have it exposed through the video. Naturally, I'm going to go ahead and roll that key here very soon, but the idea is you want to make sure that these are secure. If you don't have them secure, you might actually rack up a huge bill that is unexpected because you leaked those keys. Now, with that out of the way, let's go ahead and create our Jupyter notebook that will actually implement this. Now, in my case, I actually closed out the terminal window itself, and I'm going to use VS Code as my terminal window. So go ahead and get used to the process of toggling this open. That is Control tilde. I'm going to go ahead and run Jupyter Notebooks in here now, and I'll go ahead and open this up. Okay, so opening it up into my browser, I'm going to go ahead and get rid of this basic chain one. I don't need that anymore, so we'll go ahead and delete it altogether. Now I'm going to go ahead and create a new one, and I'm going to call this 1-LangChain LLM with OpenAI. Something like that. So the idea here is we want to use the OpenAI LangChain reference. So if we go back into the LangChain documentation, we can see that providers is right up front. We can see the OpenAI one, and we can see this is how we install it. Not surprising here, we actually already did this process. So if you actually look in requirements.txt, it's already in there. And so is something called Python decouple. Python decouple is a way to load in environment variables like OpenAI API key. That's for those of you who aren't already aware of that. So we want to load in those environment variables. The way we're going to do that, of course, is by going back into our notebook here, and we're going to go ahead and use from decouple import config. Now, the reason I use config is because I can actually pass in something that I might need, right? Like ABC might need, and go ahead and run config, and it gives me this undefined value error. This error is telling me, hey, I don't actually have it in here, which in the case of our OpenAI API key, what we hopefully have is it is in here. Now, for some reason it's not in here, what you might need to do is actually restart your Jupyter notebook altogether just to make sure that it does read that env file when it comes through. But now that I do have it in here, I can actually just set it equal just like that. You don't want to print out this API key inside of a Jupyter notebook either, because that exposes that key as well. Though the things that are output here do get output inside of the actual Git repo as well. So the next part of this is actually to use the OpenAI package inside of LangChain itself, which, what do you know? Right below the installation process, it shows you how to import the chat OpenAI model. So we'll go ahead and copy that. We'll bring that in here. Really straightforward and simple. I'm going to go ahead and run this. Now, the parameters that we need to pass in here are going to be given to you. I'm going to tell you what they are. API key being the OpenAI API key, just like that. and then the model itself. So you pass in the model. In our case, we'll use GPT-4o. You can use 4o mini as well. I've had better experience or better luck with using 4o because it's just a more robust model. But feel free to play around with the different LLM models in here, right? So there's a lot of different LLM models. This is not an embedding model. This is an LLM model only. Okay, so that's what we are going to end up using. Now, I actually don't like hard coding like this either. The reason being is if I ever need to change the model or have it based off of environment variables, I want this to be a little bit more reusable. So the way I do that is by saying LLM config and do some sort of dictionary here that will have these same values, but as key value pairs. So we come in here and just change it into being key value pairs by doing OpenAI key as a string and then putting it in with a colon, and then the model also as a string and then also with a colon. And then we just go ahead and initialize it just like that. And now we've got our model. Okay. So again, it's an LLM model. You could call it chat as well. You could call it whatever you like. I'm going to just stick with model for now and set it in here because this is just a variable on how we're going to go ahead and execute things for this model. So if we actually take a look at the OpenAI part of things, the actual OpenAI Python package, this is all we've done so far. So we've done the client part of things. Now we need to do the chat completion part of things. Now this might change over time, but for now what we're going to do is from LangChain _ core .messages, we're going to import human message and system message. Okay. So this is how we can actually start prompting this out. Now do keep in mind that what I'm about to do is coming directly from the LangChain documentation. So feel free to modify it based off of that documentation. But the idea here is we set out a few messages that we want to pass in to our OpenAI model. Whatever this model ends up being, we're going to have a few messages in here. So we'll do our system message first. And we'll go ahead and pass in the content that we want. And then we'll go ahead and put another one after that for our human message. Content again. Okay. There we go. So this content, I'm going to go ahead and change it to say translate from English to Spanish. And it's going to be hi, exclamation mark. Those are the messages I want to use for my system. At this point, what I just defined in the OpenAI equivalent are these messages. What do you know? Not a whole lot different. That is, of course, on purpose. The human message is the role of user. The system message is the role of system. This same concept is similar with other LLMs, except written differently. What we've got with LangChain is, well, now it's going to be consistent. Notice that this is LangChain core, not coming from OpenAI LangChain. So these messages can be reused with other, LLM classes in LangChain. That's kind of the point here. Next, what we can do is we can invoke these messages by just doing result equals to the model itself, the model up here, dot invoke, and then passing in those messages in, hit enter. This is going to call the LLM and it's going to give us some sort of result back, which gives us an AI message result back with the content itself. Now, one other thing that we can do is we can actually use a parser in here for this result. So we can do from LangChain core dot output parsers import. We're going to import the string output parser. Okay, and so now I'm just going to go ahead and initialize that as parser being this string output parser. And then I'll go ahead and do parser.invoke and the result itself. This will give me that actual result. This is where LangChain comes in. Okay, so we've got, OpenAI's chat model. Then we have our parser in here. Notice that we called invoke 2 times. I can chain these things together by doing chain equals to. We can grab the model itself. Then we can pipe it using a pipe, a line that goes up and down. It's right above enter. We can pipe it together. These things are now these two classes kind of intertwined together. then I can actually bring in my chain. Using that chain, I can do invoke the messages that I have, run that. That is LangChain right there. It took these messages and then it piped them in through these two places. That is actually really, really cool. Now, the other part about this, again, is, hey, what if you used a different model? That's what you could do. You could go back into the documentation and you can take a look at all of the different models that are in here. So say, for instance, you wanted to go into the Anthropic model, wherever that might be. Let's go ahead and do Claude. Nope, Anthropic. Oh, it's right at the very top. Anthropic model, install it. There's Claude. There we go. That's our model. So I'm actually not going to implement it, but I will show you the example of what you would end up doing is you would basically go ahead and run that. Now, granted, I don't actually have it in there, which is why I'm not implementing it, but you could call this the Claude model, and then you would just swap out, boom, just like that. And so you could kind of see now is you could also have this logical query stuff where it switches out the different models as you see fit. You can also chain them together and use both of the models if you wanted to, which is so, so cool. And one of the reasons that I think LangChain has become so popular is this ability to just use these as different building blocks on how they start working. Now, of course, we can do things a little bit more advanced than this, and let's take a look at how to do that by actually adding in prompting into the mix. Now we're going to take a look at how to do prompt templates. So this is the same notebook, I just renamed it, and I didn't do anything other than that. And so now I'm going to go ahead and rerun a bunch of things and just kind of illustrate what it is that we're working towards. So if you have a regular string of text and you wanted to say something like template, and we said, hello world, how are you? And we actually wanted to change world into some sort of variable, and you can say a name, right? And so in straight Python, we could just do .format, name equals to Justin, which is my name, and I could go ahead and run that. Now, another way to do this would be to actually turn this into values, as into a dictionary itself, and we could say something like name and Justin, and then we can actually unpack these values in this format call in here as well, assuming that things are formatted correctly. And that this is actually how we can use templates inside of Python. This template itself could be stored into a file, and you could open it up, and you can do all sorts of robust things with this. This is sort of the building blocks of things like Jinja 2 and Django templates, right? So those are kind of the building blocks that we've got here. But the idea is this is how we want to think of templates inside of, using LangChain. So that's what we're going to do now. So instead of how these system messages are right here, we're going to use that same concept that I just went over. So the way we do this is from LangChain, then _core.prompts. We're going to import the chat prompt template class. And then right above our messages here, we'll go ahead and start this process. So I'll go ahead and do my system, and we'll go system and prompts. And this is going to be equal to that template. So it's going to be very similar to like what we had here with the translate from English to Spanish, but I'm going to use something closer to the documentation, and that is just simply translate into the following language. Notice that I have curly brackets on here, and if I were to run .format, language equaling to Spanish, it should give me the actual value back, right? So if I run that, there we go. So of course I don't actually want .format in here, I just want the actual prompt template itself. Okay, great. So now with this in mind, I can actually do something like prompt template and set it equal to the chat prompt template class. And then we do .from messages. And these from messages in here, we pass in a list of messages. These messages are like system. So we use system and then the system prompt. And it's going to be a tuple in here, or a tuple if you're familiar with that pronunciation. And then we pass in our user. In this case, we'll pass in another one, which I'll just go ahead and say like input text, right? And so that's now my prompt template. And so to use this prompt template, what I can do is I could say something like this. I use prompt template.invoke, and I pass in a dictionary that replaces these brackets here, the curly brackets, just like format does. So we can do language and Spanish, and then the input text being hello there. And now I can run that and I can see these system messages. It actually yields basically the same result as what we had down here when we hard coded it ourselves. So in other words, we now have a prompt template that we can use going forward. So let's go ahead and comment out our old messages here. We don't need them any longer. And of course, I'm not actually going to invoke them in my model anymore or take a look at that result. In fact, I will probably get rid of all of these things right now. So let's go ahead and trash them. And so we've got our string parser here still that I'm still going to use. And so there we go. And so now we're looking at our chain. So the way our chain works now is we can actually bring in our prompt template at the very beginning. And then when we go to invoke it, it's going to be invoked based off of, well, the same thing as the prompt itself. So I actually don't need to invoke the prompt anymore. I can just pass that in as my message. And so once again, we've got key value pairs in here. I run this, and now it's going to give me something very similar to this. And we can say something like, what do you like to eat? And, if you're familiar with Spanish, which I am not, you would be able to grab that. And so what we could do is invoke it again and now change it from Spanish back to English. So get that result, whatever that is. And we'll go ahead and grab this in here. And now I can run that string. And now it says, what do you like to eat? Cool. So it actually does it. And let's leave it in as a string itself. And there we go. Great. Fantastic way of translating things. What if we wanted to translate it into a completely separate language like Italian, right? And I don't know if that's actually true or not, if that's correct, but we'll do the reverse here and we'll see if the reverse gives us that answer. And it seems reasonable. If you know these languages, please let me know if this is a good translation. But overall, the idea now is this is our chain. We now have a little bit more of a structured format that will be inside of our input. Now, granted, we could always improve the system prompts and we could do additional things to it, right? So we could add in additional languages in here, like translating into the following language 1, language 2, language 3, and then that would be the result. And of course, you could play around with that on your own. And so now we're actually starting to see some of the advantages of, well, hopefully starting to see some of the advantages of using the LangChain stuff in here. So I'm going to go ahead and delete out some of these things so we can really just hone in on the things that we want to use pretty much going forward in terms of how our LangChain stuff works. And so I'm going to go ahead and put the model and the parser right up there. There's our prompt, and I can get rid of Anthropic stuff, and there's our chain being invoked. Take the phrase, the dog ate my homework, and the phrase, the homework ate my dog. Now you already know these are wildly different, but let's see how Python might treat them. So first off, of course, we define the phrases. Then we turn the phrases into lists. We separate it out into each word. We lowercase each word so we can just have it all sorted. And if we take a look at this, they are identical. This, of course, is a huge problem because these aren't identical at all. While the text is the same, the actual text values in there, it doesn't take into effect the sequence or the context as to when this text is happening. So the dog ate my homework and the homework ate my dog is drastically different, and we need Python to be able to understand this. Now, the way we do this is by using embeddings. Embeddings will take the text, turn it into a numerical value. That numerical value will actually represent where it exists in all of text, in all of English, for example, or any other language. So it actually allows us to then compare these things. So what we want to do now is actually do that process, actually have the ability to compare different things in here. The way we're going to do this is we're going to create an embedding based off of any given text with OpenAI. Now, this process itself can be used inside of a lot of different sources. It doesn't have to be used just with LangChain, but the concept needs to be understood so that when you actually go to create vector embeddings, you have a better idea of what's going on. Now, how the embedding is created itself, well, that's going to be different depending on which model you're using, right? So the different models have different implications on how accurate these embeddings are, which we'll talk about in just a moment. But the first thing that I want to do is I want to import Python decouple, import our OpenAI key, create an OpenAI client. This, of course, is coming directly from OpenAI. It's not using any other third-party dependencies other than the raw tool itself. So OpenAI, Python decouple, and then we'll use NumPy in just a moment as well. And so what we've got here is we have this function. This comes directly from OpenAI. So if you go into their embeddings there, you'll be able to find this function in there somewhere for Python itself. There it is right there. So it's literally their example of how to create an embedding on their service. This, of course, could change over time. And there's other ones out there. There's something called sentence transformers, and you can look up that one as well. This is an open source version of that same thing, and the general idea is basically the same in there as well, is you want to take some raw text, and you want to turn each piece of those raw text into embeddings, which is what we do right here. So we've got a bunch of raw text that's loosely related to each other, and we can see the embeddings in here, and this is what one of those embeddings does. So it quite literally has numbers. I believe it's from -1 to +1, and pretty much every sort of float that goes in between. And so this right here is a vector. This is actually kind of hard to understand because look how short the documents are here, right? The cat jumped over the dog. This is tiny. This is not very much text, but the embedding itself is huge. This is a really big embedding. This actually has more to do with the embedding model than it does with the text itself, as we'll see right now. So if I were to import NumPy, I can see this is the shape of that embedding. This shape right here is also known as the dimension. This will become really important when we start using a vector database to actually store these embeddings. But right now we've got this shape here. Where did this number come from? Like, where could you find it without necessarily creating all these example embeddings? Well, you can take the model name. You can do a search on OpenAI, ideally the actual documentation of OpenAI, and eventually what you'll find is the value of those embeddings. So here's the length of the embedding vector, or the dimension of the embedding vector: 1536 for small, 3072 for large. Now that's what the current state of the art is according to OpenAI. This is definitely going to change over time because we want to make these embeddings more and more accurate over time. And that's what's happening here with this large one as well. And so this embedding vector is much bigger than that sentence transformer one that I mentioned before. And so more than likely, it's going to be a more accurate embedding. I'll explain that in just a moment. But the idea here is we've got 1536 for this embedding itself. And what do you know? If we look at the shape here, 1536. So that's actually the result. When we pass in a document or some string of text, the result is going to be that length of some kind. Great. So now what we want to do is with each one of these embeddings, I just want to compare them. The way we compare them is by using something called the cosine similarity or the cosine distance. Both of them give us roughly the same exact value, except, of course, in my case, I actually just rounded them up just a little bit to give them more of a percentage of the value here. So this will actually calculate how similar they are based off of their magnitudes, right? So the magnitudes, that is without direction, then it actually takes into account their actual direction, so you can see how similar they actually end up being. That is, if you think about a chart itself with X, Y, and Z with negative and positive, it's like which way is it going in there? This is essentially doing that calculation. Of course, you don't have to understand this exactly. You just need to understand the implications of it. So if we were to create this function here, we can see when we compare the embedding to itself, it's 100% match and it has zero distance. So it's 100% similar and it's not far away at all. It has zero far away because it's literally the same thing. But then when you compare it to the next string and the next one, they are quite a bit different. So if we come back up here, we can see the documents. The cat jumped over the dog is very similar to the cow jumped over the moon, although it's a cow and a moon. A moon is much different than a dog. If I were to change this to something different, maybe I would get a different result or a different actual calculation as far as the distance or similarity is concerned. So here we go. We can actually test that out now with the query string, the moose sat by the turkey. We can actually go through here and we can see how similar it is to these other documents, right? So what happens here is we take a string, we turn it into embedding, and then we compare those embeddings to actually find the similarity here. Now, modern vector databases do this for you. You pass in an embedding most likely, both to store and also to query, but the actual calculation will be done on the vector database to make sure that it's actually really, really seamless, as we'll see very soon. But the idea here is then we can actually compare these two phrases again, right? So if I come down here, grab these phrases, and I just put in to being the embedding and the embedding, we can go ahead and calculate the embedding for them by passing those phrases in and using that get embedding function. And so this will give us those embeddings. Now we can actually calculate how similar they are using embeddings instead of using just simple Python. And so now when I run this, we get somewhat of similarity because they still have homework and the dog, but they're not 100% similar. They're not the same at all. And that is why we actually end up using these embeddings themselves. So let's say, for instance, the dog ate my homework and then, burped it up. The homework ate my dog and then burped it up. We now see it's even more similar, but it's still not the same, right? It won't be the same until we change it to something different. We could change it to something like the cat ate my homework. This is going to be probably, well, in this case, it's not more similar than the dog and homework because we now have a different animal in there altogether. So that's probably not that surprising. We can now say maybe the red dog ate my homework. This one's probably even closer to being similar. And then we can say the pink dog ate my homework. Those aren't that similar, which is kind of surprising. But the idea here is the fact that we can compare different texts using embeddings, and we do it with the context that it exists in versus the Python way of doing it, which would be to kind of separate things out and try and compare them there. Now, of course, we could probably build out all sorts of logic to figure out how similar these things are in Python. But as soon as you deviate, as soon as you add something different, something that maybe the logic didn't account for, like red dog or green dog or something like that, as soon as you add those things, then the actual logic way of doing it kind of goes out the window. That's where embeddings have to come in. It gives us a representation of this text as numbers inside of some sort of dimension. Then when we go to compare them, the embedding dimension and the comparison dimension have to be the same. Otherwise, we'll have some issues. In other words, you can't actually mix the embeddings from OpenAI, the small one, with the large one. You also can't mix it with sentence transformers. You can't mix those embedding sizes. The shape needs to be the same shape all across the board when you go to actually do the comparison itself. Which is why we're talking about it right now, is so that you have a better sense as to what's going on under the hood. We've got text, raw text, that gets turned into an embedding. That embedding is going to be turned into that by a specific model. Once you do that, we're going to store that into a database. Then when we want to do a vector similarity or some sort of semantic search, we need to make sure that the same embedding is being used to do that search. Otherwise, they're just not going to be the same sort of vectors, and we'll have issues actually finding the correct values when they are correct. Okay, so now with this out of the way, let's actually put it into a vector database, and so we can see the same sort of concept here in place with a production-grade vector database, of course, from Upstash. Let's take a look. Now we're going to look at how we can persist our embeddings, how we can store them into a database that we can access outside of our Jupyter notebooks here, right? And the big key of this is that if your documents start to grow in scope, as in you have thousands and thousands of rows or even millions of rows, you need something that's performant in both in terms of storage, actually keeping it available for you and ready, but also in terms of actually querying, actually doing that cosine similarity that we already saw so that you can do queries really, really quick. And the way we're going to do this is by using Upstash. Of course, I partnered with them on this one, but they also have a vector database that's built in, and it's a very generous free tier, so feel free to log in to upstash.com, create your first index. This is what we're going to go off of. Now, the region itself, click a region that's near you. I'm going to be using US Central 1, and I'm just going to call this my hello world. We're actually going to delete this index at the very end of this, but the idea is we want to name it, give it a region that's nearby. Then we notice this custom embedding model that you can add in. So here's a few examples of current state-of-the-art open source embedding models that you can use in lieu of what we've been using. We've been using the OpenAI embedding model only because it's one of the more powerful ones, and also it's not really that expensive to actually get some of these embeddings done. Notice the dimensions here. So the dimensions are quite literally for the one we've been using, at least at this time. So of course, if you need to go back and figure out what those dimensions are, you can just create an example embedding, and then you turn it into a NumPy array, and then you use .shape, and that will give you those embeddings, especially if you're using the open source ones, and maybe it's harder to find what the actual embedding number is. Even OpenAI, it's kind of hard to find what that dimension vector was. But the idea here now is going back into Upstash, we need to make sure we have the correct dimensions. And hey, what do you know? There is that cosine metric. You can use other metrics to do querying as well. Cosine similarity, I think, is one of the most popular, if not the most popular. And so I'm going to go off of the free plan, as you see. I'm going to go ahead and create this. And this is going to give me a few different things that are important to actually get this configured. One of the main things is these two environment variables that we want to grab and bring into our .env file. So I'm going to go ahead and paste these in here, and then I'm going to go ahead and actually grab them from the Upstash console in just a moment once that vector database has been provisioned. There it is. So first off, we grab our endpoint here. Notice I'm just calling this the Upstash Vector REST URL, and then I've got my token here that I can copy as well. Now, what I did was basically exactly from their documentation here. This is what we're going to be working off of to a degree. So I'm going to go ahead and copy this as well, and we'll go ahead and bring it into our notebook towards the bottom. Notice that I already have the index in here with those values, but that's essentially what we're going to do is we're going to upsert our vectors. We're going to go ahead and either update or add them into this database using something called an ID or some sort of ID field. Now, what this will emulate is if you're using some other kind of database in conjunction with this vector database. So this vector database is serverless, so you only pay for what you end up using. But the idea is when you want to have a bunch of different documents, you might be pulling from another database storage of some kind. Maybe it's a SQL database, maybe it's a NoSQL database. Either way, we want to actually have the ability to apply an ID so that we can update a individual row instead of updating all of them at any given time. So that's what we're going to do. I'm going to go ahead and kernel restart and clear this all out just to make sure that I have my Upstash Vector configuration items in here. Looks like I don't have them yet, so let me just go ahead and save them in my .env. That's probably why. So let's go ahead and restart it again. And so at this point, they should be in there. And sometimes when this happens with Python decouple, what you often might have to do is actually close out your Jupyter notebook and then just open up a new virtual environment in here and then run Jupyter notebook again. Okay. I mean, you could always hard code these into the notebook just to get the proof of concept, but make sure that if you do hard code them in there, that you delete them when they're done. Okay, cool. So restarting the notebook is how that solved everything. And so once again, we're going to go ahead and create all of our embeddings. This time, though, I'm going to go ahead and create it into being a data set. So the idea is just iterating over their positions, and that's going to be their ID. We can always change it if we want to. But once I run through there, I can see that if I look at data set, of 0, I should be able, actually the actual number 0, I should be able to get the actual value for that. And we could do that with all of the other ones in there as well. Great. So that gives me my actual ID. And so to use this inside of Upstash, what I want to do is I want to use this index upsert here. So what I'm going to do is I'm going to cut this up and paste it in there just to connect to the index. I shouldn't have any errors at this point. But now I want to run through the embeddings that I've stored in this data set. So if I do for key value in the dataset.items, we should be able to print out the keys. And so we can actually think of this as my ID is equal to that key of some kind. Okay. And so what I'm going to use is the vector class, although you can just pass in a tuple here of the actual vector itself. But what I want to do is I want to have it a little bit more explicit so I know exactly everything that's going on in terms of the key value pairs or the arguments that I want to start inserting my data into the index. So first off is the vector ID. Then we can pass in the vector itself, which of course is going to be the actual embedding model itself. So if you actually want to make it a little bit more explicit, what you would end up doing is you would use a data set of some kind that has the ID and has the actual embedding in there. In other words, you would iterate through the data set and you'd get the ID, and then you would say embedding equals to, some value dot get embedding. But in our case, we're just doing it as key value pairs. So there we go. So we've got our embedding in here, and that's going to be our vector. So all I want to do now is say vectors equals to just an empty list here. And then we're going to go ahead and append all of these vectors in here like that. And now what I should have is a list of Upstash vectors that are ready to go. Okay, so as we can see here, it's not a whole lot different than our actual embedding dictionaries, but now it's based off of the vector class that Upstash Vector uses. Now, for those of you who maybe have some errors with Upstash Vector, make sure your requirements.txt already has it. Ours did. We did that a long time ago. But the idea here now is I have a data set of vectors that I can now add into our database. And the way we do that is by using upsert. This, of course, is going to either insert the data or update the data based off of that ID. So I'm going to go ahead and bring in my vectors in here, and then we'll go ahead and paste that in. There we go. So we now have our success of our vector itself. So the final thing is actually doing a query. Notice that there's a vector in here. Now, we actually already saw this before, which was grabbing a query string. In this case, I'll say the moose is sat by the turkey or something like that. Okay, so there's our query string. We need to turn that into a embedding. So query embedding equals to get embedding of this query string. And that's going to be our query now. And then we can just go through in here and we can actually do our query. And we can say the top similarity ones, or the top K, we can do 2 of them, although there's only 3 items in there. So let's just do all 3 so we can see what that response is. This is now querying into our stored vector database. As we can see with our usage in here, we've got 3 requests in here coming through, which makes sense based off of everything we've done. But now we can actually see the result. So if we go ahead and do results equals to that, and we iterate through these results, do for result in results, we can print out result.id and result.score. And we can take a look at this again. And so, oops, maybe a little spelling error there. And so we can see now the similarity between all 3 of these items from those vectors. This isn't going to be a whole lot different than what we've already done. But now what I want to do is just take one little change, and we're going to go ahead and change one of our dataset items. So I'm going to change dataset 2. So let's go ahead and up here, and we'll go ahead and say dataset 2. This is going to be a new embedding. So the string itself is going to be very similar to what we've done. I'll do get embedding, and I'll now say the moose sat near the turkey. Okay, almost identical, but it changes the data set a little bit. And so with that in mind, we're going to go ahead and use the vectors again. So I'm going to go ahead and do something similar to this, but just using the vector directly. So go ahead and grab that dataset element here. So this is it. So we're going to go ahead and grab dataset of 2, and that's going to be the key value pair that should give us that value, or rather that key. So that actually should be into our vector, and the ID itself should be 2. And so we're going to go ahead and give this a shot in terms of our vector. If I run that, I see ID equals to 2, and there's my new vector. So once again, we do, index.upsert, and then vectors equaling to just this one single vector in there to update that single vector. And then we can run this query again. This time it's a 98% match, right? So if we multiply this by 100, we can see how similar it is. Now, the things that I don't need to continue to do with my search is I don't need to continue to get that query embedding. I can just keep using it. This will do that search for us. And so you can really play around with this in terms of how you generate or change things with your data set. Let's change it. Let's add a new data set item in here and say the moose sat near the turkey. Let's go ahead and say it by the dog or something like that. Now I'm going to go ahead and upsert that one. Oops, we want to change this to 3 and 3. We upsert that one now. Moose sat by the turkey. Now it's got 2 of them that is very similar to, although not identical. Very close, but not identical. Cool. So now let's go ahead and do by the dog. This one is identical, so we should get a identical match. sure enough, we do. Cool. So going forward, as it relates to LangChain, what we end up doing is we can turn all of our data, all of our text data, the unstructured text data, this could be blog posts, this could be PDFs, this could be a whole lot of things. You could turn that into embeddings that then get stored in your Upstash Vector Database so that when we use LangChain to do searches into this data, it can actually do this same sort of querying on our behalf when we add some sort of prompt in there or do some sort of question that actually makes sense for the actual data set that we have, which we don't really have one yet. But the idea now is we have the ability to use this vector database, and we can use it anywhere just as long as we have the URL and token. Off the video, I deleted the old index and created a new one in Upstash, mostly so I could have clean data and have no other data sets in there whatsoever. And then also do keep in mind that I'm using the same dimension count that I was using. So what I want to do, of course, is actually bring these new values into my environment variables here. So the first one is going to be our Upstash Vector REST URL, and then our token, Upstash Vector REST token. And let's go ahead and make sure that that's the correct one. There we go. And so now with that in mind, I'm going to go ahead and refresh my Jupyter notebooks by running Jupyter notebook. And there we go. This will open it up for me. And then I'll open up into a brand new notebook with just a few things involved. Now, what we're going to be using for our data is this Wikipedia package. It's a little bit older of a package, but the idea is we need big data sets. Feel free to go and take a look for bigger ones. Kaggle has a lot of different data sets you could consider in there and just to download as well. But in our case, we're going to be using the Wikipedia one because once you have it installed, you can do things like searching for a specific page. In our case, we're going to be using different cities and just go based off of that. So we can just do some generic searches inside of these cities. But as you notice here, this is massive text. So there's a lot of text going on in here. We need to actually adjust that as well. And we need to be able to handle large text inside of our vector database by splitting it up by tokens, specifically using tick token, which is from OpenAI that allows you to really see what's going on, how many tokens you're going to end up using, as we'll see here. As you may be aware, LLMs have a token limit, the amount that you can actually put into any given LLM. The amount of text that you can put in there is limited by the number of tokens you can pass in. But before we actually do the token splitting, what I want to do is I actually want to kind of go off of what we just did with the Upstash Vector Database, where we used Upstash, Python Upstash, to actually create our index and add in our embeddings and doing all of this stuff. So we want to do something very similar to that by using LangChain's version to do it now. So in order to do this, of course, you need to make sure that you have several things installed, which we already did with our requirements. LangChain Community is one, Upstash Vector is another one, also just generally LangChain itself, and then LangChain OpenAI. So we definitely need to make sure that we have all of those things installed. Of course, I'll throw in some references for them right here as far as the docs for the Upstash Vector Store inside of LangChain. So the first thing that I want to do is I want to actually bring in the OpenAI embeddings from LangChain itself. We've already seen the embedding model that we want to use. I'm going to go ahead and copy and paste both of them that you might consider. Now, of course, if you use the bigger one, it's going to cost more, and you're going to need to update your index on Upstash. If you don't update that vector database, then yeah, you're going to have issues with using the different embeddings. I repeat it only because it's really important. Okay, so next thing is what we need to do is we need to import our Upstash Vector Store from LangChain Community. This import has changed over time, and I would imagine it might change in the future. But the idea is we want to use it to actually implement our store or our vector store. Now, I'm following convention for LangChain here. This is almost exactly from the docs itself. But the first thing is we want to use the embedding model that we're going to use, which of course is this one right here. Notice that they're not actually embeddings. There's no embeddings actually coming through, even though the variable name is the same as one we used for actual embeddings before. We're not doing that anymore. We're going to go ahead and let the LangChain Community Upstash Vector Store actually do the embeddings for us. So the next thing is we want to pass in our index URL, which of course is going to be based off of the Upstash Vector REST URL. Let's bring that one in there. And then our index token, which is also going to go ahead and take in this token. Now, these vector stores are actually really nice and they can be reused in many different ways. You can use other ones as well on LangChain, but overall, this is how you're going to go ahead and set it up. So now we actually have that vector store. So all we need to do here is create documents and implement them. So when I say documents, I mean documents that are similar to what we did here. So we need to do something very similar to that. Now, before we get to that point, let's actually do a search for different things on Wikipedia. So I'm going to go ahead and do Wikipedia search, and I'm going to do Boise, Idaho, and do a quick search in there just to make sure that I have some things in here related to it. Doing that will prevent errors if you end up trying to use it inside of the next part, which is going to be just our raw documents. And I'm going to use an empty string here, and then I'll go ahead and do my cities, and I'm going to put it equal to these two values that I just did, which was New York, New York, and then Boise, Idaho. So in the case of the search, I'm actually using whatever this value is right here, and that's what I put into my cities value, not my raw documents. There we go. And so what I want to do, of course, is I want to iterate through for city and cities. We're going to go ahead and grab the value then. So the page is going to be the Wikipedia page, and then the title being the city itself. And then we can append our raw documents in here with that content. So we would do raw documents.append page.content. Okay. So that's definitely one way on how we could do it. We get those raw documents, and this is going a lot closer to what we did over here. But we can also include metadata. We could have with pure Upstash itself, we could have other metadata in there. In our case, I'm actually going to go ahead and now use the LangChain document. So I'm going to go ahead and bring this up right above here. This LangChain document class is very similar to the vector class we were using before. This case, we actually aren't going to be passing the vector. It's going to go ahead and create it for us. So now I'm going to go ahead and just change this to being simply documents. And I'll go ahead and comment this out. And we'll do doc equals to document. And then we're going to pass in a few arguments in here. So the first thing is going to be our page content. And of course, that's going to be page.content. Now, this is actually like a Wikipedia page result. So not to confuse things too much here in how the documents work, the page content is going to be that result. Next, what we can do is we can add in some metadata in here. This metadata helps explain what's going on with the data set that we have. This is going to be really important later when we want to see where any given piece of data is coming through. So we can add in the source. In this case, I can add in something like the Wikipedia page results, and we can do .url. And then we can also add in a title in here. And this, of course, is going to be the city itself and any other metadata we might want to keep. Now, in the case of the source, the URL is actually the key thing that we're going to use. So then we take that document that we create and we append it to our general documents. And so I run through that, and then that might take a few moments because it's actually doing a search. And if we look in here and we do the zeroth element.metadata, what we should see is that metadata for all of these items, right? So if I were to iterate through all of them, I would see all of the cities and the sources that come through here. The big problem, though, is this data is still far too big. So that's why we need to split it by tokens. We're going to be using tick token to do this, and it's essentially this right here. And so this will allow us to then split the tokens and then actually implement them into our vector database. So we need to split them first, and there's a lot of different ways on how we can split them. I'm going to split them based off of the token splitter here, which I'm just using one that's just slightly different than that. And the way we implement it is going to be just like this. So we get our document loaders, the text loader itself. Actually, don't know if we need that anymore. But the token text splitter from tick token encoder. We pass in the model name we want to use. This, of course, is going to be our, let's say, for instance, our OpenAI LLM model. We can just set that in there as well. Make sure you get the correct values here. Otherwise, this splitter is not going to work correctly. And of course, you also want to make sure that you have tick token installed as well, which is just as simple as pip install tick token. And that should already be installed in my case. And if it's not in our requirements, we should probably add it in there as well. Tick token. Great. So with this text splitter now, what we want to do is we want to use it to actually split up the documents. The final documents we'll implement, which is going to be docs equals to the text splitter and then split documents. And in this case, the actual LangChain documents, these instances right here, all of these documents here, we're going to go ahead and pass that in here. This will actually split up all of those documents in there. We can take a look at the length here. Let's go ahead and do the length of these docs. We see it says 312, where the length of our other one is going to be quite a bit different, and that's going to be 2, right? So it's quite a bit different of a response. But doing this will allow for us to actually meaningfully query this actual data set, this storage value that we're going to end up using by just doing inserted vectors. And this is going to be equal to store.add documents and then the docs themselves. We run that. This is going to insert them all into our vector database index, very similar to what we did before when we wanted to insert them as well. So when we added the vectors here, we've got all of them. If I scroll down a bit, I will then see index upsert. This is actually adding in various vectors. So is this. So we just did that same thing. And we can also verify this inside of Upstash. We can see the request, how many data items in here. What do you know? 312. What do you know? 312. So it just added in the exact document count that we just had. So in this case, our actual vectors are stored all chunked up. They're all chunked a little bit different than what you might want with other kinds of data sets, right? So in other kinds of structure, you might not want to chunk them like this, but inside of a vector database, especially one from Upstash, this actually works really well. So it's now chunked out in terms of the actual tokens that we'll end up using. And so with this in mind, we can now do a search on our store. So the search itself, let's go ahead and say result equals to the store dot similarity search. And now I'll go ahead and say the city with big buildings. This one is obvious to all of us. Of course, that's the point, actually, is to give us a very obvious result in here. And so we get a bunch of New York City results in here. But this actually doesn't give me a score, so I'm going to go ahead and comment that one out. And then we'll actually do it again. This is a similarity search with score. This actually gives me that score in there. And so we can actually iterate through all of our results for that. And we can see the actual score itself. So if I run through this city with big buildings, here is the score. Now, in this case, I could just result to New York City. What about city with trees? I mean, they both have trees, so ideally they have both of them. Now, in this case, I know Boise well because it's the city of trees. That's what it's named after. The city named after trees, right? So, boom, Boise. There we go. Now, it's interesting that New York's even on there, but it's probably because there's a lot of trees in New York as well. So, it's not like there isn't. But if we do K2, now it actually just returns, just Boise. The top two are Boise. And these are, of course, different actual inserted documents. They're different rows in our data. And that's why it actually has it repeated. So it feels like it might be duplicating the result of the data, but it's not. It actually is returning back the correct data because of those chunking, because of splitting the text up. And we had a lot of data. And of course, if you were to add more cities in here, your search will be really pretty good. I would say it would be amazing. But the idea is, of course, now we can actually start piping this in with LangChain. Now we're going to go ahead and create our LangChain plus Vector Store chatbot. This, of course, means that we're going to be chatting with the data we stored inside of Upstash Vector. Now, this is actually going to be fairly straightforward. First and foremost, we need to create our store or the instance of it so we can actually access this instance. Now, do keep in mind, we also want to turn this into a retriever. So very similar to like when we went to search for it by using the store, we can actually use it as something called a retriever. This will allow us to actually pipe it into a chain itself, right? And so we do it as retriever, then we do our search type being similarity. Then we are going to go ahead and do our search keyword args, and that's going to be K being like our top 2 responses there. Okay, and so we can use this retriever similar to like what we did before, but now I can just do retriever.invoke and say something like, what is the city with the most trees? This response may or may not be good because they both have a lot of trees. It's saying New York. What is a city named after trees? And now it's saying Boise. Great. Okay, so that is our retriever. So once you can see that you can do .invoke, that's usually meaning that you can actually chain it together with LangChain. So what we want to do then is actually build out a LLM that we can actually have conversation with, and it will decide whether or not it needs to retrieve things and how to interpret what it ends up retrieving. So let's go through this process by first off importing LangChain, the OpenAI, and the Chat OpenAI model as well. I'll go ahead and do my LLM config. This is going to go ahead and pass in a few keyword arguments here. So the model that we want to use. In this case, I'm going to use a very simple model, which is GPT-4o-mini. Then I'm going to go ahead and do my API key. And of course, we'll pass in what the API key was from OpenAI. There we go. There's going to be our configuration. Then I'm going to go ahead and initialize our LLM with the Chat OpenAI class here. And then we'll go ahead and unpack all of the arguments in our LLM config. Now, do keep in mind the tokens we actually ended up using was GPT-4o. These actually shouldn't make that much of a difference in terms of our LLM. The mini is probably not going to be as accurate as 4o, but it's going to be a lot more inexpensive or a lot more affordable. Okay, so now we've got 2 things, an LLM and a retriever. Next, what we need to do is create a prompt. So the prompt we're going to go ahead and use is the chat prompt template like this. And so the actual chat message I will use is going to be fairly straightforward. Answer this question using the provided context only. So the question and then the context. So for that, we will then go ahead and pass in the prompt itself, which will be from message human based off of these messages. We've already seen some of this. So there's our prompt now. Now, the next question is really going to be around these arguments here for that prompt. So the way we do this is called a runnable pass-through. And I'll just give you an example that's from their docs. But the runnable pass-through is you can actually use it to create new data. So we passed in the number being 1, and once it's modified, it gets to be 2. So if we multiplied it by some other value, and then we put in here some other value, it will actually run that for you. So LangChain has the ability to do this. Why this is important has to do with our prompt, the context, and the question, so that we can actually use our retriever, or we can invoke our retriever inside of our chain. And that's really the key here. And so our chain is going to be something like this, where it's chain, and it's going to be equal to a dictionary in here. This dictionary is going to be the context, which is this right here. And that's going to be our retriever from above. And then our question is going to be our runnable pass-through instance here. Then we're going to go ahead and run our prompt after that, then our LLM. And then we also probably want to bring in a parser. So I'll go ahead and bring in our str output parser as we've seen before. And here is our new chain. And our prompt is not defined. It looks like maybe I didn't run that cell. Let's run that again. Now we can run chain invoke. And where is the best place to eat, and in why? I invoke this and we get a issue with some of our context here. Let's go ahead and see why. And we've got our question, runnable pass through. And here's the problem. This should say context, not content. Let's go ahead and run that again. And now when I invoke it, the best place to eat in New York is subjective. Awesome. That's actually pretty good. Where's the best place to eat maybe pizza in New York? Also still subjective, but it's going to give us some other things in here. The context does not have a particular place to eat pizza. Okay, cool. So what type of food is best known in New York, or NY? NY, of course, being the abbreviation for New York, which may or may not be in that context. But there we go. We've got a bunch of different things that are in here. What about in Boise, right? So once again, it's going to go ahead and search for Boise. Basque food, interesting. What about we do something like Austin, Texas? Now, as you may recall, I actually did not provide that context at all. And there we go. We get a response back saying it's not available to us, which is pretty nice. So the reason this is actually different has everything to do with the LLM itself. The LLM is going to answer any given question you pass in here, whereas the previous search, when we actually did our semantic search, which is what's going on within our LangChain documents. Let's go ahead and scroll down here. This right here is a similarity search. This is a semantic search right here, where this right here is performing a semantic search, but it's also going to infer the response from that semantic search based off of this prompt right here and based off the fact that it is a retriever. But now we can just chat with this data as we see fit to get more and more context. Now, the nice thing about LangChain is if we wanted to extend this, we can make this even more robust by adding in other kinds of maybe pass-throughs or other kinds of LLMs, or even a search query where it can actually search a search engine itself. There's all sorts of things you can build on top of this. Now we're going to start the process of building out our LangChain chain API service. So the idea here is we're going to spin up a minimal REST API that will allow us to call our chain with our input, which is really just that one single question. And so we want to start that process now. There are some things that we've already installed, one of them being LangChain serve. This is what we'll end up using to actually serve a playground that we can use when it comes to LangChain itself. Before we get there, though, we want to actually start off with FastAPI and UVicorn. If for some reason UVicorn is not working on your machine and you're using something like Windows PowerShell, which of course I do recommend WSL, check out Waitress. Waitress might actually end up working for you just fine. I think UVicorn will have no issues, but this will actually run our application for us. It will run our FastAPI application. So with this in mind, let's go ahead and just create a minimal FastAPI application for those of you who may have not done it before. So we'll go ahead and install Python or the pip install requirements.txt just to make sure that FastAPI and UVicorn are in here. So let's go ahead and do our minimal setup with creating main.py. First off, we're going to go ahead and from FastAPI, we're going to import the FastAPI class from the FastAPI module. We'll initialize it with an app, just like that. We'll create our first API route with api.get, some sort of path that we want to support here. And then we'll go ahead and just call this something like our home page, and we'll return a dictionary of simply hello and world. After we do that, what we can do is we can also say if name, as in the two underscores or the dunder method, is equal to main. This is where we'll go ahead and import UVicorn and run UVicorn.run of the app. We can declare our host here. In our case, I'm just going to go ahead and use localhost, and then we can also declare a port. In my case, I'll use the value of 8100. So this is where you would end up using Waitress if that wasn't working. You can also use FastAPI's command line tool stuff, but I'm just going to use it all in this one single module just to make things a little bit more simple for us. So with this in mind, I'm going to go ahead and run Python main.py, and of course that's going to start my server, which I can open up, and there we go. There's our hello world minimum viable API that we might want to build out. Now do keep in mind, this is still just Python. There's nothing about this that can't be modified for a more full-featured web framework like Django or whatever might come. FastAPI is just a minimal framework and just makes it really easy to build out your different APIs that you might want. So for example, if we take this home page here and we just copy the URL here and not open it, hopefully, and run curl on that URL, which for some reason it's opening. Let's go ahead and just do localhost 8100. This curl command will actually simulate as if you were doing an API request right there. So of course, now what we want to do is just modify main.py to work with our chain and specifically LangServe. LangServe and FastAPI work out of the box together. So let's go ahead and take a look at what that looks like. With our Jupyter notebook still running, I'm going to go ahead and jump into the LangChain and Upstash Vector Chatbot one, and we'll go ahead and just do file, and we want to download. You can also do export notebook as, and then basically look for an executable script. That's actually what we'll end up using. This will give me a Python script in my downloads that I'm going to go ahead and drag on into my project here, and I'm just going to call this my helpers.py. Now, normally I would probably build it out to make it a little bit more full featured than just helpers.py. The only reason I did this is because I already wrote a bunch of code that I can run. But of course, this means that I want to get rid of a bunch of things and reorganize it as well. So it's just a little bit more script friendly or user friendly when we go forward. Okay, and so that's what we'll do now, and just go ahead and get rid of some of this. Put this up here. There we go. And notice these little run blocks here. This is because it's from Jupyter Notebooks. So the VS Code is automatically trying to assess that Jupyter Notebook stuff in there, which of course, it looks like I might have deleted some things that we actually still need, but we'll bring it back once it's necessary. Okay, so there we go. We've got our chain at the very bottom. That's the key. We need our OpenAI key, which of course was all of this stuff. I think I accidentally deleted those. I probably don't need to set OS Environ on here, so I'm not going to. And then we've got our chat prompt template. Looks like everything's imported as needed. Looks like maybe we're still missing something. Let's go ahead and grab these embeddings here. I didn't think I deleted that much stuff, but let's go ahead and bring it in. So we've got our store, and there's our string parser here. Yeah, it looks like it didn't actually bring in our retriever, unless I deleted those. But nevertheless, we want to make sure we've got all of the things that we needed to use in here in our chain itself. Okay, so basically what I want to do is I want to use this chain. I want to actually return the chain back. So I'm going to just define get chain in here, and all I'm going to do is return back the actual chain itself, just like that. Okay, so everything else I think we have imported up, and we should be good to go in terms of our imports. Let's go ahead and actually bring this chain into main.py. So I'm just going to go ahead and do import helpers. And now what I'm also going to do is I'm going to bring in from LangServe, we're going to import add routes here. So what we can do with add routes, this is built into FastAPI. We can actually use this and come down here underneath any other defined routes. We can do add routes of the app. So let's go ahead and break this down a little bit. Of the app itself, the chain that we want to use, the chain that we want to pass, and then finally the path we want it on, which we're going to go ahead and call it just simply chain. So the chain itself is of course inside of our helpers. So helpers and get chain. And that should actually grab that chain for us if we did everything correctly, of course. So now that we've got that, we should have a new route here. I'm going to go back into my FastAPI application. I want to restart this, mostly because I'm using UVicorn right inside of main.py. If you're using UVicorn inside of the command line, you probably wouldn't have had to restart it. But once I did restart it, I see that I've got LangServe in here, and there's a playground for our chain at chain/playground. Pretty cool. So let's go into our FastAPI application, go to /chain, and here I've got nothing found. But if I go to /playground, hopefully what we'll see is our actual chain, right? And so a big part of the reason I actually have my helpers separate, or actually loading in that main chain separate, is mostly because this is all based off of what we've already done. Like this Runnable right here, we probably don't need in there. We could probably get rid of a bunch of other imports in here as well. Looks like our chat prompt is in there. I'm not sure why it's not green, but if I close that out and open it up, yeah, it looks like only the OpenAI one and this OpenAI one are not in use. Okay, and so the import OS also not in use. So this helpers right here, I could probably actually import into a Jupyter notebook as well without needing to do much modifications. So main.py is just meant to be really, really simple in here. What you might find on the LangServe docs is all of this stuff in one place. I just wanted to make sure that it wasn't too complicated in terms of actual FastAPI. But the nice thing is, if I come back in here, what is the city of, or the city that never sleeps? I think they would refer New York as that. Maybe it's a different city, but there we go, right? And so what is the city that is named after trees, right? And of course, it's going to be Boise. And then tell me about Los Angeles. Right. Something that's not in our context that we know about, it's not in there. It does say stuff about New York City being related to Los Angeles, but does not have details about Los Angeles. We can also see all of the steps that LangChain is taking to make all of this happen, which is also really cool. So it gives you a lot of insight as to what's happening with the chain itself. So let's say, for instance, which is larger, NY or Boise. Right. And so in terms of landmass, Boise is probably higher, maybe, I don't know. But it doesn't actually give us that comparison, so we don't have that data, which is interesting that that's not in the Wikipedia article. But, you know, what is the population of NY? Let's go ahead and do that search now. And there we go. Yeah. And what is the population of Boise? And yeah, quite a bit smaller in terms of people. So yeah, I think overall, I'm surprised it can't actually do that comparison, how it's built out. But that's not really the point here. The point here is that we can build out this chain and then we can continue to iterate on this chain. Now, the next real thing that we would want to do is have a route that just calls the chain directly, like an actual API route. So let's see how we might go about doing that. Now we're going to use Python request to do an API call to our LangChain chain. Now, the idea here is, of course, you should have Python requests already installed. We're using the Jupyter Notebook mostly to test this out. You can do this on pretty much any module. Now, Python request, since it's used by so many packages, this is the only dependency you would need to call your LangChain API, assuming that it was deployed somewhere other than our local machine. But we're going to go ahead and emulate our local machine as if it was deployed somewhere, but we want to call this chain here. So what is really cool about LangChain serve or LangServe is this add routes actually gives us a few things in addition to just the simple playground. So we saw /playground already. We went and opened that up and we took a look at that. Now, the other ones that we have is invoke, and this is going to be how we call it. There's another one called stream, and there's even one for batching, which we are not actually going to look at. Now, actually, the API endpoint does not have a slash, and it is going to be /chain/ whatever that ends up being. So our route here, the fact that we put this path here means that we need to actually access it with chain in front. Now, the nice thing about this is if you wanted to have different kinds of chains or multiple chains in there, you could do that. You could have a bunch of routes with a bunch of different chains. That is completely up to you on how you end up building that out. But to keep things simple, we're going to just use chain invoke. We'll start off there at least. So our endpoint is going to be our HTTP //localhost at port 8100. Okay. And now we want the actual chain itself. So we'll also do /chain. Now we want to do our type that we are going to use. So we'll go ahead and say our chain type or our request type, which is going to be just simply /invoke. So our actual URL endpoint is going to be taking in our base endpoint here, and then we're going to go ahead and also use our chain type. And so just giving us this final URL that we'll have in here, which making sure that we actually have quotes at the end of all this. There's our final endpoint. Next is going to be our data. Now, in our case, we just need to pass in input. That is something like or tell me about New York, right? And you could probably even misspell it, but that's going to be our data. So to use Python requests, we'll use r equals to requests.post, the URL we're going to post it to, and the JSON data that we want to send. And then we can just expect back JSON data, which of course, if I post this to my endpoint, it's going to invoke that chain, it's going to run it, and then it's going to give me a bunch of response in here. Super nice that this actually ends up happening. It's a very simple way to make all of this end up working. So then we get our output in here, which we could also just take a look at by coming down here and taking a look at that output. There we go. Right, so the cool thing about this is now you can integrate this anywhere. It doesn't have to be just in Python, right? So the key part is that we invoke the chain with this URL, and then we pass in the data of, this input. So if we wanted to take a look at this as another method that you might end up using, you might use something like curl with a capital X of post. Then you can post to that endpoint. So let's say, for instance, if I post to that endpoint with no data, I'll get this value here. If I pass lowercase d and then JSON formatted string, which starts with a single quote, inside we use curly brackets, then our key value pairs are going to be with double quotes in there. Then we pass an input and then something like tell me about the Big Apple, and then run that. We will then get a response back. So then again, showing another way to do our API request into any given endpoint. Now, we can also use the streaming one as well. So if I change it from /change/invoke, we can actually do stream, and this will actually stream back the responses. Very similar to like what you might be used to in terms of any sort of the LLMs with their browser interfaces. They usually stream back the response where it's almost like it's typing as it's coming through. So you can always do that as well. That's what that stream does. And then batch just allows you to have a lot more things. Now, the idea here is we can also use something from LangServe, the client side of LangServe. So we can also use LangServe in another format, which is not needing to just use requests. This is really nice, but if we wanted to just take it a little bit further, we'll take a look at how we can use LangServe's client to do these LangChain requests to the LangChain server side. LangServe also has some client-side code that we can run that allows us to do LangChain-like things with our remote API, as we'll see in just a moment. But the idea is if you just installed the LangServe client and you imported the remote runnable class here, what you could do is just say chain equals to remote runnable of the chain endpoint. Now, the nice thing about this is then you can have multiple APIs that you might end up doing or multiple chains that you might end up doing, and you'd be able to switch to them at any given time. Now, of course, you could do that with Python requests as well, but using this, we can just do something like invoke and tell me about NY or something along those lines. And so invoking this way does that same request. It will actually request the API service and give some response back. So the other thing that's nice about this is we can obviously do all of the streaming things as well. So if I did for chunk, let's say for chunk in the chain itself, and then .stream, and did something like, what do you know about Boise, right? And then print out each chunk, we could see those things coming through in real time, right? And so there's also an asynchronous version of both of these things. So we can grab the invoke one here. I'm going to go ahead and let's comment this out for a moment. And we can do await, and this is just simply a invoke as an asynchronous invoking. This is nice for asynchronous code if you ever need to use it. Of course, Jupyter has this by default. Jupyter is running asynchronous code already. But you could do the same sort of thing with the streaming as well. So what you do with a for loop on streaming is you do async for chunk in chain dot astream, and then you can print out all of those chunks as well. Again, just using asynchronous code if you want to. Now, these things are built in by default. This is the support that LangChain Serve Remote Runnable has, And of course, you could just install it with this. So if it was me and I wanted to use this in something like Django, this is what I'd end up doing. Just this one single package and having it call my FastAPI endpoint that's deployed somewhere, and I use that remote host and all that. Now, realistically, what I would probably deploy it to is Kubernetes so that I don't actually have to expose this to the internet at all. Or at the very least, a VPC type system with a virtual machine so they're all on the same resources and they can communicate over something very similar to localhost instead of the internet. Okay, so the idea though is once we have this chain, can we do something more? Can we actually chain this remote runnable to something different? And the answer, of course, is yes. So what we can do now is we can do something like from LangChain and _core.prompts. We can go ahead and import our prompt template. Now, the important part about what I'm about to do is the fact that when we invoke our actual runnable, our remote runnable, we just pass a string. This is the very nature of our actual chain as it stands right now. The fact that our chain has this context and question just like that is the reason that we pass it in as a string, not any other reason. So since we pass it in as a string, I'm going to go ahead and say something like this for my prompt itself. So tell me about topic. And then what I want to do is I actually want to format this prompt. So the idea being that now when I go to actually grab the prompt, I get the string of it itself. Now do keep in mind, this is for reusability. If I wanted to use this prompt in other chains altogether, this is what I would end up doing, something very similar to this. Next up, what we want is we want our runnable pass-through. So if we go back into our code here, we have our runnable pass-through that we're going to go ahead and use. I'll bring this into my import here. And now we're going to go ahead and do my new chain. I'll call this my new chain. And this is going to take in the runnable pass-through, piping in the format prompt, and then piping in our main chain, or our remote chain, if you will. This will allow me to then use, this should say prompts. This will allow me to then use just the topic. So now I can do new chain, invoke, and then just pass topic and do whatever topic query I want to put in here. So I'll go and say NY and then tell me about topic. I now can invoke that, and that will actually call that old chain as well. And if I said something like LA, this will likely not have anything to respond back with because it won't have specific information about Los Angeles. Super interesting that it does take that context that we have, which is just two cities, and it infers LA as in Los Angeles, which is something pretty cool. Now, that might not happen for all city abbreviations, but it's pretty nice that it has this. So if I did something like London, it would probably understand that it's going to look for that city based off the context as well. And there we go. Cool. So I can go ahead and say Boise food, right? And it's going to invoke that. And now I can just do it based off of the topics, and I can add the prompt in as I want. Now, if my remote runnable, if it was different, if it was designed differently, then you could pass in different kinds of context and not necessarily have the parser like we do. So feel free to play around with this. Now, the other nice thing about remote runnable is you can actually proxy it, as in you can put it inside of another API service and run it through there, which is what's exampled here inside of the LangServe examples themselves. You can just put in remote runnable in there, and this would be quite literally that same chain. You would just need to update it a little bit so that it ends up proxying it correctly overall. Something worth trying out if you wanted to, in terms of just adding yet another layer of data. But it's really cool that we can actually do this from a client perspective and only just really needing our remote runnable to be able to call it. All of the other chaining things, of course, use LangChain, but we don't necessarily need all of our third-party dependencies in here either. So if you were to use this into Django and you wanted to abstract away like some of the things that we did, as in like if we look at our helper here, if we were to put it in Django, another FastAPI program, or even use it on a JavaScript version, which can do this as well, you've got this idea that all of your chat OpenAI stuff is abstracted away. You don't need to pass in any of those keys. Also, the Upstash Vector Store, also abstracted away. You don't need to pass in any of those keys with just using this remote endpoint itself. Really, really cool. And using this remote endpoint, the other reason I said Kubernetes or at least a VPC type service on the deployment side is then you also still don't have to worry about it being accessed from the internet. But of course, if you wanted it to be accessed from the internet, what we would want to do is implement rate limiting. And that's something we'll do in just a moment. I'm not going to cover the authentication stuff because it adds in a whole other dependency, which would be like a database or an SQL database of some kind, or even a NoSQL database. Instead, what we're going to be doing is we're going to be implementing rate limiting using just purely Redis and Upstash. Let's take a look. When it comes to building out an API service, it's a really good idea to start implementing rate limiting. All this means is that you actually keep track of the number of requests that come through so that if they have too many requests in a short amount of time, you can prevent them from doing more requests. So the way we're going to do this is by implementing Redis. So go into your requirements here, go ahead and use Redis, and then run pip install -r requirements.txt to make sure that Redis is installed. When we actually use Redis, we can actually keep track of things like visits really fast and really quickly and really easily. So what I want to do is I'm going to import from Redis. We're going to import the Redis class. I'm going to go ahead and implement my Redis instance here. And we're going to see just some basics of using Redis as a key value store to, well, upticks a number over time. So to actually create this Redis instance, we're going to go ahead and go into Upstash, of course, upstash.com, and using Upstash Redis, we're going to create a brand new Redis database. I'm going to call this try LangChain, and we'll call this our rate limit or something like that. And we'll select a region. Ideally, you select one that's near you. Go ahead and create it, and then go ahead and grab the credentials for that region. So in my case, I can jump into Python. I can see I have Redis running right here. So I'm going to do something very similar. I'll go ahead and grab these values here, and we'll bring it into our code. So naturally, I don't actually want to have my hard-coded values in here. So another thing I'll add is from decouple, we're going to go ahead and add in config, and then I'll just go ahead and actually move these into my .env file right now. Now, I already actually added these things in here, but we're going to go ahead and do it one by one together. And we'll just go ahead and say config is the Redis host. And we probably want to cast it as a string. The port, this is actually the default port, so I probably don't even need it in my environment variables, but I'll go ahead and do it. And we'll call it Redis port. We are going to cast it as an integer, and we'll do our default here, which is, of course, 6379. You'll see that in a lot of places, but it's not always that port. So I'm going to go ahead and add it in as my environment variables here. And then, of course, the final one is going to be our password here. I'll go ahead and cut this out, bring it into my .env, and then we'll just go ahead and use that one in here as well. And we'll cast it as an str. Okay, so how do we actually use Redis? Well, Redis is a key value store. That is, we need to know what key we're going to store something into, just like a dictionary. It's actually pretty cool. So what I want to do here is I'm going to call this first one, I'll call it my visits key, and I'll just call it visits. That's it. So this is kind of general visits key, and I'll use my Redis instance to get that. So I'll go ahead and say current value equals to the Redis instance.get visits key. What do you know? Simple enough. With that, I can also then go ahead and say Redis instance, and I can use something called increment or incr. I can actually increment the key value or whatever that key value would end up being. And then I'll go ahead and say my final value, and this is going to be equal to that original request here. And I'll go ahead and grab that. And then we'll go ahead and say something like visits, and it's going to be that final value. Now, of course, I actually didn't set the initial value. So what if the current value is none? So if current value is none, then we need to set that value. Now, the cool thing about Redis that we can do is we can do redis.set. We can grab the key, and then we can set the current value. Now, since I'm going to increment it right after, I'm going to go ahead and set the starting value at 0 because the increment's going to happen in just a moment. Then I can also set an expiration as to how long this would end up being here. So I'm going to go ahead and put 10 seconds. So that means that in 10 seconds, this will be gone. So let's go ahead and run our server again. And we'll go into our local host, just to our home page to see this value come through. We see that if I refresh in here a few times, it's going to start counting these things up. But in a very short amount of time, that thing is going to be gone. And so if I actually go into Upstash, maybe by the time I actually look in here, the visits are now gone. They're now zeroed out in here altogether. So we can think of this zeroing out kind of like a window of time that will be limited, that will have a rate limit. So now what we can do, of course, is just go back into our home page and update it so that we can kind of give an instance of it being limited, like, max requests. I'll set that equal to 5, for example. So this final value, we want to see if it's maxed out. So we'll go ahead and say do rate limiting being false. And then I'll go ahead and do something like try, and basically saying do rate limiting equals to the integer of the final value. Because again, if it's empty, then there is no final value. And we just want to see if it's greater than the actual maximum requests. Otherwise, we will just go ahead and say pass. And then we will go ahead and say something like limited and passing in do rate limiting. Now I'll go ahead and run this all over again, and we'll take a look, and I'll refresh in here a number of times. So ideally speaking, when we first start, it's going to say no, and then over a short amount of time, it'll then say yes, it's limited. And then of course, if I wait that window duration from when it was first set, then I'll actually be able to see the actual value itself, right? And so you could have a rolling window as well. Instead of using increment, you could use set every single time. So you would just increment to the current value, set it, and then set a new time, which would actually, push it forward. We don't want to do that. We actually want the rate limiting to start from the very first request, so we can actually have a cumulative amount of requests that are coming on. Now that we understand how to work with Redis a little bit more, we're going to go ahead and do our FastAPI middleware to do the same sort of thing, but then return back different responses if we have too many requests in a certain time window. So the way we're going to do this is by using the default middleware that FastAPI has, which of course you can always copy and paste from their documentation. But the idea is we declare the app middleware of HTTP. We need to import the request class in here. I also need to go ahead and do from fastapi.responses, we need to import a JSON response as well, as we'll see here in just a moment. So one of the things that's important when it comes to our requests here is, well, we need to make sure that we're still returning a response. Middleware requests, or when you would work with middleware, you can do stuff before a request happens, you can do stuff before the response happens, and then you can do stuff before the response is returned. And so what we want to do is in between the request and the response. That's the idea here, at least. Anyway, so now we're going to go ahead and do our rate limit middleware. That's what we'll call it. I don't need to do the start time or end time. That's not necessary. You could do something like that, but we're going to go ahead and say our rate limit is equal to like 5 requests. That's like 5 requests per window or per time. That time is going to be our rate window and however long you want it to be. In our case, we'll go ahead and do 10 seconds. Right, so we're doing 10 seconds to actually store the request itself. So what we saw before was we actually have this visits key in here, and then we can actually do our different rate limiting things in here. I'm actually going to go ahead and cut that out of the homepage view because we no longer need that. I'm going to now put that into my middleware view, and we'll go off of this key to start out with. So visits key is going to be in here. Then we're going to go ahead and set that instance. That's correct. The final value, whatever that ends up being, is going to be up to the rate limit. And then, of course, the rate window is right in here. And then our max requests, this is going to be, well, how many requests do we actually want to use? I don't need that anymore. That was from the other view. We've got our limit and our window. Those are the terminologies that you would use for rate limiting. And so what we've got in here is if we've got if rate limiting or if do rate limiting, now we're going to return a different response. The response itself is going to be a JSON response with a status code of 429. And that's it. And so we can also pass in some content in here and say something like error and, rate limited, something like that. Great. So our JSON response comes in, and let's put a comma between those things. And there we go. So let's go ahead and give this a try now. So let's make sure our server's running or refreshed. Let's go ahead and do that. And so here we go. And then now I'll go ahead and refresh on my home page here. And I'm going to do it only a few times. I shouldn't have to go that many times because now I automatically get these too many requests coming through because my limit is so little, right? So little in such a short amount of time. So 10 seconds isn't that long. So I should be able to request this again here shortly, but then I do a few more requests. All I'm doing is refreshing the page a number of times. We will see that it is rate limited here very, very quickly. Now, the other thing is if I go into my Jupyter notebooks, I have a notebook that really just calls the endpoint itself. It doesn't call the chain or anything. I can see that rate limit come through in here as well, right? So eventually we will see that one. We're getting the wrong status code in here from the front end, which is interesting. So I'm going to go ahead and restart this and we'll run them all again. And so I should get 429, but I'm getting a 405 call here. Probably because it's not rate limited yet. Maybe that's why. Because I can't actually send a post method to that URL. So let's go ahead and try this again. There's my 200. And eventually, there we go, 429. Okay, so I was setting the wrong method in, but now we've got our do rate limiting. This is now working. There's one more thing that I need to improve here, and that's going to be our visits key. For that, I'll just use a simple change for the time being, which will be an API key. Let's take a look. Now, it's really cool that we have a rate limiter, but this is more of a global rate limiter. What we want to see now is the process that we would have to basically create an API user. Now, this API user is going to be environment variable based, as we'll see in just a moment. But the idea being we can have different API keys for different users. So the rate limiting is to that specific API key versus to just any API key or any sort of key visits like what we've got here. So that's what we want to do now. The way we're going to do this is by creating an API access user and an API access key. These things are, of course, injected into the runtime. So it's not exactly user authentication, but it will allow for us to have a more robust rate limiter, especially in a microservice like this. So let's take a look at how we're going to do this. First off, our API access user, I'm just going to go ahead and say Justin. The API access key is going to be the key one. So to do this, I'm going to jump into the terminal. We'll open up Python, and then we're going to go ahead and import secrets. And then we're going to do secrets.token_URL safe and do like 32. And there we go. There is going to be our API key. And so there's other ways to build out API keys as well, but this one is fairly straightforward, especially because we all have Python at this point. So now I want to use this API key inside of my main.py, inside of my FastAPI application. So naturally what we could do is we can actually bring it in. So API access key equals to config of the API access key. And we also might want the API access key user. So same thing, also config of API access key user. Great. So now what we want to do is we want to have our rate limiting based off of these two values. So how do we actually find if the request that's being used has those two values? Well, the way we can do this is by actually accessing request.headers. So inside of FastAPI, you can actually look for headers and custom headers at that. So in our case, we're going to go ahead and create a custom header. So we'll call this our API key header, and we're just going to give it some name. Most of the time, what you would end up seeing is x-some header, right? So basically custom header in here. There's a lot of different ways in how you could think about doing this, but usually it's prepended by x-. It's usually not some header. Now, every once in a while, some programs automatically will create the X for you, but in our case, we want to go ahead and say X API key. That's going to be the header we're going to look for here. So we'll go ahead and do request headers .get of that header, and then I'll also want to just print out that fact. Great. With this in mind, I'm going to go ahead and close out Python here. I'll go ahead and run this app with python.main.py, and I'll go ahead and also run our Jupyter notebook. Now, writing the Jupyter notebook right now has the added benefit of having all the environment variables in there. So we should be able to access them in a new notebook. In my case, that notebook, I have the secrets in here that you could always reference if you'd like. But there we go. We've got our API access key in here, and this is it. Now, granted, this is not something we'd want to share, just like any other API key, but we want to see how this ends up working. So in our Python request here, I actually am not calling the chain endpoint at all. I'm calling the base URL. So we can even put the chain endpoint down here, and we can run this, and we should be able to get a status code of 200. So it's just doing a simple request, as we've seen before. This simple request is going to our home page, this right here, and it's going to go ahead and do the rate limiting itself for that old visits key. And so what we should see here on the FastAPI runtime is we should see that there is no API key header. It's none. So in other words, what we want to see now is we'll go ahead and say API key equals to this header. This will actually give us that key value pair. And if there is no API key, we want to return something back. So if API key is none, then we're going to go ahead and return a JSON response. And we'll go ahead and do our status code of 400. And then we can do a content of something like detail. And we'll go ahead and say invalid API key. Great. So now if we were to run this again inside of our Jupyter notebook, I got to restart the API key service. So let's restart FastAPI and let's run it again. Now we get a 400 error because we don't actually have an API key. Even though I have these headers in here, there is no actual API key that's coming through because we have the wrong name in here, right? I put a string of API key header on purpose so we can see that it's working incorrectly. So going back into our project here, we can see that the header is now being passed. It is in here. It's really that simple. So if I run it now, I should actually restart the FastAPI application again. But now let's run it again. Now I should get a 200 status code because we now have that header in there, which is great. Now, of course, if we wanted to extend this to doing the remote runnable, if I were to try and run this now, I will get that same error, that 400 error in here. Because the remote runnable uses something very similar to Python requests. I believe they use HTTPX, but whatever they end up using in there, we still need to actually pass in that API token. Now, one of the ways we can find out what that would be is by running help on the class itself, and you can actually see some of the things that are brought in there by default. Notice that headers is one of them. We have cookies, we have a few other things in here as well, but headers, the fact that headers is in there, it's probably going to work the same way as Python requests, or more realistically, the same way as HTTPX, because even in the response, we can see that it is using HTTPX when it go ahead and does the request. HTTPX is basically Python request as well, just a little bit different. But the idea is here, now I can pass in that header, and I should be able to invoke the remote runnable as well. So this should also take hold for when we actually apply a rate limiting key here. So at this point, all we've done is checked if the header is there. We haven't actually validated whether or not it's the correct header. So the next thing is if the API key is not equal to, well, our actual API access key, then we can go ahead and do the same thing. This is an invalid API key, but this time it's more of a permissions problem. We just change the status code so us as developers know that it's incorrect. Like this one doesn't have one. This one is saying that it's probably wrong. Great, so that's just another way to check that. Feel free to go back into the Jupyter Notebook to see if that ends up working. But there we go. So now we've got our API key. So the next thing is here, if the API key matches, we're going to go ahead and go off of the API key user. So now what we want to do is I'm going to call this my rate limit key. This is going to take in, I'll say rate limit, and then the value of the user I'm using, which is going to be this right here. Now do keep in mind, if you are getting an access key in here, you could also do something like, valid API keys, and then pass in the access key as a value, and then doing the username in here somewhere like this. So like if we went ahead and did like that, we could then do a key value pair lookup to find who the user is based off of the key that's being used. Or you could also store this in the database as well. What I'm just going to use is the environment variable ones because it's fairly straightforward. But the idea is we want a unique key for the API key user. And that's what's happening here. So this rate limit key is going to replace what we used to have. Now, I also want to have not just the rate limit key, but the access total key, something like that, where it's API access of that same user, right? So basically tracking how much access they do as well. So what we want to do here is, assuming that we have these two keys, I want to get their current values. So we'll go ahead and get our, I'll call this our RL current val, as in our rate limit current value, which of course is going to get our Redis instance, and it's going to grab our rate limit key. More than likely, that's not going to exist yet, so we'll go ahead and grab that rate limit value, and then once again, we will go ahead and set the rate limit value. We will set it based off of, well, the rate limit key, and then the rate window. So this is still doing the same things that we've already seen. Next up, we want to go ahead and set up the total access value as well. So I'm going to go ahead and use this once again, and I'll actually go ahead and bring it right underneath here, and we will go ahead and grab the access one and just change these things a little bit, and I'll go ahead and say access current value, bring that in, and then I'll go ahead and use the access total value. Now, in the case of access, we want to track it for all time, always. So I'll go ahead and get rid of the rate limit window. I don't need a window anymore. I just need to make sure that I have the access itself. So basically, if that is none, oh, these should be is none and is none. There we go. So that's setting them. Great. So now what we want to do is we want to see, we want to auto increment this because we're starting both of them at 0. So I'll go ahead and grab the instance itself. We're going to go ahead and use the first one, which will be our rate limit value. We want to increment that. So I'll go ahead and bring this up right after that clause as well. So there's our rate limit stuff. Now what I want to do is I want to see if the rate limit issue. So basically this whole thing right here. I'm going to paste this up here and say do rate limit. Everything's in here just the same, roughly speaking. But of course we want to get that current value or that final value again after it's been incremented. We'll go ahead and grab that one for that key. And then we've got our final value in here. And there is our new rate limit stuff. So if it's not rate limited, then we would go ahead and increase the value down here for the total access key as well. And now it's got all of that. So we could do another rate limit on general access so that our system doesn't get overloaded if we wanted to. And of course, that's how you would go about doing it. But I'm not going to do that general access one. I'll do it based off of individual users. In our case, we only have one user, so it's not really general access, or it's already general access as it stands. But now we've got it based off of an API key, an API user, and all of that, and also all of the rate limiting. So let's go ahead and refresh this again. Now what I'll do is I'm going to go ahead and run some of the requests in here, and we get a 401. So we're using maybe the wrong access key in here, so that's interesting. Let's go ahead and see the access key, the API key. Let's print out both of those things just to make sure that we are getting these values in here. So let's go ahead and run that again. And there we go. So we've got the correct value for the API key, but the API access key is not giving us the correct value, which is interesting. So let's see in here what's going on with that. And let's try this again. I'm going to go ahead and print out the API key and print out the API access key. Save that. And let's run this again. Okay, here we go. 401. And I print it out. It just says, it's not actually coming through at all, which is curious that it's not running an error in here at all. Okay, so what I'm going to try here is I'm going to go ahead and close out that virtual environment, and let's go ahead and try and run it again just to see if it refreshes all of the API tokens. And we'll run this again. This time it works. Great. So of course, if I were to run this a few times, jump into Upstash real quick, I can see the rate limit in there. It's going to go away within 10 seconds. So if I refresh in here, it's probably zero again. But API access, on the other hand, has a bunch of items already in there. Of course, it's not tracking timestamps in there. It's not tracking every single event, but it is tracking global events. So we can actually start to get a sense as to what's going on. And of course, this will also work with the remote runnable as well. So this should be, one of those things where depending on how much we're using the API, the remote runnable will also eventually get a 429 error or the rate limit error in here. I might need to update the window here. Let's go ahead and update it to, let's say 30 seconds for 5. And then we'll go ahead and rerun this again so that we can see that it is being rate limited on both of these things. I'm going to go ahead and do 4 there, and this should be 5, and then I'll run it again, and hopefully it actually does rate limit the runnable. And there it is, being rate limited right there. Too many requests for the runnable. That's exactly what we want. This is now an API key based rate limited FastAPI application that uses LangChain to do all sorts of cool things. So let's go ahead and get rid of these print statements in here. We're now at, I think, a really good spot in terms of where we wanted our application to be for, actually building out something a lot more functional that we can plug in to an entire ecosystem that just needs to use this one single microservice that could potentially do a lot. Granted, it doesn't actually do that much because it's only 2 cities in here, but that data part, you can add a lot of data in there and you can get some really powerful stuff going on. It's actually really, really cool. Hey, thanks so much for watching. Hopefully you got a lot out of this one. Now I wanted to leave you with one challenge, and that is building out a LangChain agent. Now the idea behind an agent is where LLMs fall short is sometimes you're missing data. Agents can actually help you with that missing data and allow the LLM to make a decision on whether or not it wants to search the internet, for example. So what we could do then is we can take our current chain and we can bring it in with an agent. So you can ask a question like, tell me about New York and its current weather. Then it will tell you about New York from what we currently have. Then it will use the agent to do a search on the internet using something like Tavily to then get a response back that actually gives you the current weather in New York. It's actually really fascinating and something that I think you are well equipped to undertake at this point. Now, of course, if you have any questions or any other suggestions on what you'd like to see covered in terms of LangChain or any other kind of tool that helps with automation, please let me know in the comments. My name is Justin Mitchell. I was excited to take you through this one. I think it's really promising as to where we're going with all of these LLMs and AI tools because they're really just helping things that much better. It already helps me so much. I'm curious how it helps you. Please let me know in the comments about that as well, and I look forward to seeing you next time. Thanks a lot.